All right, let's dive into a question that sounds like it's straight out of science fiction. Do chaos circuits dream of quantum computers? It's a fantastic thought, and it connects two fields of technology that, honestly, you'd never, ever expect to see in the same sentence: the wild unpredictability of chaos theory and the incredibly fragile power of quantum computing. So yeah, how could these two worlds possibly have anything to do with each other? I mean, think about it. On one hand, you've got classical chaos, a system that follows fixed rules but is still impossible to predict. And on the other hand, you have the quantum world, built entirely on probability and so delicate that the tiniest little disturbance can just wreck everything. It's a real head-scratcher how these two opposites could not only meet, but actually help each other out. So here's how we're going to crack this mystery. We'll start by really getting to know these two worlds. We're going to find the secret order that's hidden inside of chaos. And then we'll uncover the Achilles heel of quantum computers. After that, we'll see where they have this unbelievable collision, how chaos can actually be a bodyguard for the quantum world. And then finally, we'll take a look at what this all means for a totally new, nonlinear future. Okay, let's set the stage. It's time to meet the two main characters in our story. You've got the wild, untamable world of classical chaos and the immensely powerful yet incredibly delicate world of quantum mechanics.
Just look at this table. It really lays out the fundamental conflict, right? The differences are just so stark. Chaos is deterministic. It follows rules, but it's still unpredictable. Quantum mechanics? Totally probabilistic. Chaos comes from nonlinear equations, while the quantum world is run by linear ones. They are, in almost every single way you can measure, polar opposites.
So, to really get how they connect, we first need to understand each one on its own turf. Let's start with chaos. What do we actually mean when we say a system is chaotic? It's not just a mess. Well, the absolute core idea is something called initial value sensitivity. And what that means is, even in a system with super simple fixed rules, the tiniest, most microscopic difference in where you start can lead to completely different results down the road. This is precisely why trying to forecast the weather weeks in advance is, basically impossible. And this quote just captures that idea perfectly. It's from the meteorologist Edward Lorenz, the guy who actually discovered this whole phenomenon. And it isn't just a pretty line of poetry. It's a really powerful metaphor for how a cause that's almost too small to measure can have a massive, completely unpredictable effect. You've heard of it. It's the butterfly effect. But here's where it gets really mind-bending. Chaos is not just pure randomness. The path a chaotic system takes will never repeat, and yet it's always pulled toward this very specific, elegant shape called a strange attractor. It's this beautiful, complex, fractal structure that shows us that deep inside all that unpredictability, there's a hidden, profound sense of order. Okay, time to shift gears and meet our second world. Quantum computing holds this incredible promise, right, to solve problems that are literally impossible for today's biggest supercomputers. But all of that amazing power comes with a critical, almost fatal weakness. Now, the source of all that power is the quantum bit, or qubit. As you can see, your normal computer bit is simple. It's either a 0 or a 1. A qubit, though, thanks to this amazing property called superposition, can be both a 0 times and a 1 at the very same time. And through another trick called entanglement, you can link qubits together, so the state of one instantly, and I mean instantly, affects another no matter how far apart they are. That is how you get this massive parallel computing power. But, and this is a huge but, all of that quantum magic depends on keeping those states perfectly isolated and fragile. And here's the villain of our story: decoherence. The second a qubit even brushes up against the outside world, poof, all of its quantum properties vanish. It just collapses into a boring old classical bit, and your entire calculation is ruined. And the problem is, this enemy is everywhere. Decoherence is caused by almost anything. A little bit of heat, tiny impurities in the materials, stray electromagnetic fields, even the wires you use to control the qubit can betray it. Seriously, beating decoherence is the single biggest challenge in building a quantum computer that can actually do something useful. So, let's recap. We've got our two worlds: chaos, deterministic but unpredictable, and quantum, super powerful but fragile. And we've got our central conflict: the quantum world's desperate fight against the noise of decoherence. Now, for the big reveal. This is where it all comes together. And here it is. This is the whole turning point. The very thing that defines quantum mechanics, its linearity, is what makes it so fragile. And the thing that defines chaos, its non-linearity, That holds the key. So get this. One world's greatest weakness is solved by the other's defining characteristic. How cool is that?
Okay, that sounds pretty amazing in theory, but how does it actually work? How can you possibly use the wild, untamed nature of chaos to protect something as delicate as a qubit? Well, this isn't just an idea, it's a real, major experimental breakthrough.
And the credit here goes to a brilliant team led by Yasunobu Nakamura, who's a true pioneer in this field, working at RIKEN and the University of Tokyo. He and his team figured out a truly ingenious way to make this unlikely alliance a reality.
So here's the play-by-play. The problem is that the control line that sends signals to the qubit also accidentally lets unwanted noise in, which causes decoherence. The team's solution was to stick a special non-linear filter on that line. You can basically think of it as noise-canceling headphones for the qubit. This chaotic circuit acts like a shield, protecting the qubit from all that random environmental noise, and the result? It dramatically increases the qubit's lifespan, and it does it without slowing down the computer at all. It's just an incredibly elegant solution to a massive problem. And this is so much more than just one clever trick. This breakthrough really signals the beginning of a powerful and totally unexpected partnership. So what does this alliance between chaos and quantum actually mean for the future of computing? Well, the possibilities are just incredible. For starters, chaos circuits are fantastic at generating the truly random numbers that quantum algorithms desperately need. Second, we can start designing new kinds of qubits that are just naturally tougher, with nonlinearity baked right in. But the most mind-bending idea is this. What if we could actually control decoherence? Turn it from an enemy that destroys our calculations into a tool we can actually use in them.
Yeah, this is about so much more than just building better computers. As this quote suggests, we're really watching the birth of a whole new way of doing science. By fusing the structured world of chaos with the probabilistic world of quantum mechanics, we are just smashing the old boundaries between physics, math, and information science. And that brings us to our final thought. The real heart of this story is about taking something we all thought was a problem, the unpredictability of chaos, and using it to solve another, even bigger problem. So the question I want to leave you with is this. If the structured noise of chaos can shield a quantum system from the destructive noise of decoherence, what other so-called enemies in science are just misunderstood allies waiting for us to finally find the right connection? Thanks for joining me.